Okay, so in this video, we're going to be talking about DSC, or differential scanning calorimetry. And this is an example of a commercial DSC that you see here in the picture. So inside of the DSC chamber, there's actually two chambers. So it's a furnace that has two separate chambers. So one of them contains the sample of interest. So for our machine that we have in the lab, that is on the left side. And then on the other side, there's a separate chamber that has the reference. And this reference is chosen as something that doesn't undergo any sort of significant thermal transitions, like a change in heat capacity, like a melting or a crystallization or decomposition or anything like that. And so it's just supposed to be a baseline that we compare to. And so this DSC machine will basically, the differential part is to compare the profiles of these two chambers. So we basically scan a thermal range. So we go from, say, room temperature up to some higher temperature, and we impose a heating rate, a scan rate of some degrees per minute. 10 degrees per minute is very common. And we have both of those chambers scanning at the same rate so that they're both at the same temperature. And what we do is we measure the power needed to heat the sample and the reference. And so the differential part is that the power difference is the difference between the power needed to heat our sample and the power needed to heat the reference. And since we have set a reference that doesn't undergo any sort of transitions, then we know any sort of transitions that occur because of the sample. And so any endothermic, exothermic, or changes in heat capacity are attributed to our sample as long as the reference is valid. So that's the idea behind this differential scanning calorimetry. We have two independent furnaces, but we heat them up in the same way so that any differences are caused by the sample itself, and we can use that to identify specific thermal transitions and get a lot of useful informations about it. Okay, so like I mentioned, we have a furnace and it has a two chamber system. So this is our sample and this is our reference over here. So they're both heated in the same manner, and so that's our ramp or scan rate. So this is in units of, so it's a change in temperature over a change in time, and so we give that degrees per minute. So 10 degrees per minute is a kind of standard, but you can obviously change that. So that's kind of our default for us though. Other than this, we want to look at the melting, we want to look at the crystallization, we want to look at anything like changes in heat capacity, but we don't necessarily want to look at, for example, oxidation or anything that can happen with air. So typically we blanket the furnace with inert gas. So for us, this is nitrogen N2, but you could use argon or anything like that. And so that's just to prevent anything from oxidizing readily in the elevated temperature. So that's another element that we have here. So like I mentioned, our heat rate or scan rate is a constant here. And so if we kind of think about that as a graph, we have temperature versus time. And so that would just be a steady increase, and then that slope is that 10 degrees per minute or whatever that we use. So that's the first part that we have, and this is something that we control. We control the ramp rate, we control the temperature that it starts and ends at, and so we have control over this furnace. And again, both of these are ramped at the same in the same way, have the same amount of N2. Everything is treated the same except the power, right? So each one of these is heated electronically. So we've got a little coil underneath that heats resistively each of these furnaces, and each one of them is going to have a certain input of power to maintain this heating rate to this specific temperature. So we have to put in so much electrical power, and so that's what we measure. And so when we look at DSC curves, we're going to see power difference. And the reason we look at the difference is because we expect the reference to heat up very steadily, because nothing occurs to that sample. And so we just have to continuously pump energy into it to get it to heat at that same rate. The sample, on the other hand, there can be differences in the amount of power that we put in. For example, if we have an endothermic event, something that takes energy at a constant temperature, right? More energy, more power is going to be required to heat that sample. And so we would see a blip, particularly a peak, on that curve, because more energy is going to the sample with the reference to the reference. Same thing if we have exothermic, but in this case it'd be the opposite direction, because energy is being produced by the sample, and therefore less power is being required to heat it up in the same way. And the same thing with the change, if material goes through a change in heat capacity, we also see a difference compared to the reference. That's why we need this to be something that is very benign, doesn't go into any thermal transitions. And so we're measuring this difference in power required to heat the samples. So that's something that we measure. And the reason this is useful, the reason we measure this, is because this heat that we're putting into the system, this power that we're putting in, can be thought of as heat. And heat is equivalent to what we call enthalpy from thermodynamics. So heat is the same as enthalpy changes under constant pressure. So we are not allowing pressure changes in the system. We have a constant, atmospheric, whatever the atmospheric amount is, we have that constant. So we can say that the change in heat with time at constant pressure is going to be equal to the change in enthalpy with time. And so enthalpy is something that is calculated for various materials, for a specific event. So this heat flow, so this Q has, and it's a flow because we've got seconds, so this is going to have units of joules or millijoules, because we're dealing with so small of samples per second. So those are the units that we're going to be looking at in this type of reaction. Okay, so next, I've mentioned multiple times we have a sample versus a reference. And so it's important to kind of define that as well. And since we're looking at enthalpy that we defined in the last part, we're looking at delta of the enthalpy change for each, right? So the large delta here is for the change in the heat flow, which we've defined as enthalpy over time. And so the way we define it in these experiments is to talk about the heat flow for the sample minus the heat flow for the reference. So this is sample minus reference. So this is just the way we're defining it. And if somebody wrote it different, it wouldn't matter. It doesn't change anything fundamentally. But what it does do is it gives us sort of a convention for the peaks, right? So it tells us if we see peaks, if we're defining it in this way, endothermic peak should be a certain way and an exothermic peak should be the other way. If you change this, then everything would be opposite, right? Because the way we're defining sample minus reference. And so in this case, the positive event is endothermic and the negative event is exothermic. So this is the convention we've set by using this definition. And so that's going to be important for the curves that we see. So if I draw a kind of standard curve, so this is the change in heat flow, or again, that's the same thing as enthalpy that we have defined up here, then, and this is a function of, it can either be time or temperature, but it's almost always temperature, then we might see a curve that looks like this. So this is kind of showing you all the possible things that we could have. So based on this, there's two peaks here. This one, which is positive in the way that we've defined it here, which means that it is endothermic. And then this one is negative, so it's got to be exo. And when we have this type of, I put the last kind of thing that we tend to see, this kind of step change. This step change is a change in the baseline. And so this is a change in the heat capacity. And we'll talk about all these types of events in a second. Okay, so this is a very common curve that you might see, kind of showing really all of the types of peaks that we tend to see in a polymer sample. So obviously you can do DSC on other materials, but this is a kind of typical curve that we might see. And so then you should ask yourself, you know, we know it's endothermic, we know this is exothermic, we know this is a change in heat capacity, but what events do those tie themselves to? And so I'm going to draw it a different way because this is a little bit out of order from what we would see. So this is, again, heat flow up here. And so here I'm going to draw it, and I'm going to have this curve first, and you'll see why that is in a second. But let's say I have this curve. We know that this is exo, this is endothermic, and this is a change in the heat capacity. So you should ask yourself what each of those corresponds to. So what type of event is endothermic in a polymer? And so, or materials in general, right? You have to put energy into something for it to occur at a constant temperature. And that should be melting, right? Melting is one of those events where you have to put more energy in at a constant temperature. And so that results in a peak. So this is the melting temperature. All right, so next, so this is the opposite. This gives us energy. This puts out energy into the system from the negative peak here. And so again, you should ask yourself what kind of event, and it doesn't have to be for a polymer, it's actually just any material really, would give off energy. And it happens before the melting. And so in this case, this is crystallization. Because we're dealing with polymers that are a mix of amorphous and crystalline, this peak, if it exists, and not all polymers will have this peak, and not all polymers will have this peak, but if it has this type of peak, crystallization is a reordering of the material into this crystalline structure, and that lowers the energy of the system, and therefore energy is released. And so if you have this type, it's a crystallization event that we see. Okay, and lastly, this kind of change in heat capacity that we see over here, this also occurs in polymers quite frequently. And a change in heat capacity, if you remember from a class like ceramics, is tied to the glass transition. So this is the TG that you might remember. And so when an amorphous material goes through its glass transition temperature, there is a change in the heat capacity, which is that step change. So oftentimes it won't look perfect like this. You might actually see a little peak up here. So it goes through the step change, but also has a little bit of a peak. They're not always perfect, but that tends to be a glass transition. So this is kind of all the different transitions that we might expect to see for a polymer. If it's amorphous or has some amorphous phase, then it'll go through a TG at some temperature. Keep in mind that we're only testing a certain range. So if that material has a glass transition temperature, for example, below room temperature, we're not going to pick it up. And then if it is a crystalline polymer, there is a chance that it will crystallize after it goes through the TG. And then if it's a crystalline polymer or semi-crystalline, then it will go through a melting temperature. And so you'll see a peak there. So again, you don't have to see all of these peaks. You may only see one or some mixture of the two. But these are all possible things that we can see in our materials. Okay, so now let's go through transition by transition and take a closer look at each of these. And so let's start with the glass transition. And again, you're probably familiar with this being called TG. So at this temperature, some of the properties that change: the specific heat of a material, the coefficient of thermal expansion, volume will change, and dielectric constant. So these are all things that change. We're not measuring all of these, so that's important to mention. And so this is all because the motion in the polymer chains. So these chains that polymers are built on allow the motion of these chains becomes available. So effectively, motion of polymer chains relative to each other is now possible. So this is basically the amount, the temperature corresponds to the temperature at which the motion of chains relative to one another can become possible. And so this type of transition is a second order transition. And so it does not experience an enthalpy change. So that would be, an enthalpy change would be, for example, the peak that we saw for melting and crystallization. Those are first order transitions. So here we only see a change in specific heat, right? Which is something that changes by the step change. And so again, the way that we see this, and so if we just draw the change in heat capacity, it's going to look something like this. So we have basically the heat capacity is the slope. And so before the TG, we have a slope here. After the TG, we have a slope here. And then the step change, that's the change in the heat capacity, so Cp. And so this position where this occurs, right, that is our Tg, and we can actually obtain this change in heat capacity by how large the step change is here. So again, the change in heat capacity is referred to as the heat capacity of the sample minus the heat capacity of the reference. Same definition we used previously. And we can define the heat capacity as the change in enthalpy with the change in temperature. And so we have, we can also write that in terms of the change in enthalpy with time, so the rate, so that's a flux, times d time over d temperature, which is the scan rate, right? So the inverse of the scan rate, temperature with time. And so we can calculate the heat capacity by knowing the heat flux or rate and the scan rate. So those are the two items that we would need to know to be able to calculate this. And so the inflection that we see here, the step change, most software can measure this. So Pyrus can measure this step change that we see. And also, if you just need to know the temperature, you can do this more visually too by looking for where that inflection occurs and noting the temperature. If we wanted to get the step change, we might have to use some software. Okay, so that is the glass transition. So now let's look at crystallization. All right, so let's look at the crystallization peak. So I've just drawn the crystallization peak, and this is again heat flow versus temperature. And crystallization, this is the exothermic peak, so it's down in our configuration. So from the data that we have here, we can get the peak location here. This is TC, so we use the peak as that point. So in the software, or at home with your software, or just looking at the Excel file, you can find this position by the peak, so essentially the lowest value. So that's what the Pyrus peak software will do to determine this peak as well. So you can actually go into the data file and just look for the minimum value there at the peak. Also though, we can so if you think about the area between the peak and the background, so the area, what we normally call area under the curve, but this is an upside down peak. So this area also gives us information about the enthalpy. So basically, the location of that crystallization event can be determined by the peak, but the area can determine the enthalpy of that event. So crystallization in this case. So this will be important later on when we want to try to determine how much the material is crystallized, and therefore the crystallinity, what percent we have in this case. So this can be obtained through the Pyrus software, or in some cases with peak fitting software that you have at home by taking the area underneath the curve. So the way that this is done is that basically we set boundaries like you'll see in the the peak fitting video is that we set boundaries, it fits a linear line, and then calculates the area underneath. Okay, so we can write that out mathematically as the integral of the change in enthalpy with time of the sample dt. And so that's going to be the enthalpy of the sample. So that's why we can use the area underneath, because we're talking about the integral of this with time. So that's what we need. So as you can kind of see from this equation, since this is in terms of time and time, we'll also need a factor of the scan rate to be able to calculate this as well, because the scan rate is what gives the connection between time and temperature. So we also need to account for the scan rate in those cases. So what you'll see in most cases when you have this enthalpy is it will actually be in terms of mass. So you'll get some type of mass unit here. And so that's why the mass is so important when we calculate, or when we run the DSC, and we're always asking for the mass of the polymer is. All right, so let's look at the last thing then, the melting temperature. And then again, we call that Tm for melting. So this is the same thing as what we saw above, but the peak is positive in this case. But we can find the same features. So the peak in this case would be the melting temperature. And then if we fit a background linearly and look at the area, that's the same thing, the enthalpy of melting in this case. So the only difference between these two is the fact that this one's positive and this one is negative. Nothing else is the same. So it basically gives us the sign of the enthalpy. Okay, so based on that, I want us to think about a couple different types of polymers and how their curves would look. So let's consider two cases. Let me start on a new piece of paper here. So let's say that there's a polymer that can be crystallized, so crystallizable, but it's currently amorphous. So it's currently amorphous, but it is crystallizable. So basically, it can become a crystallized polymer. There are some polymers out there that are amorphous, but because of the structure and so forth, we can never make them crystallized. But this is not the case. This is where we have amorphous, and then it can become crystallizable. So let's imagine we have that polymer, currently amorphous, but not yet crystallized. So if we look at the same kind of heat flow versus temperature, which is our sort of standard curve. So it's amorphous, so it's going to have a TG, right? So if something's amorphous, it's going to have a TG. Again, it has a TG, but it may not be discernible on the curve here if the temperature is low. So you have to consider the range in this case. But let's say that we can see it. So the TG, and then it's amorphous, but it can be crystallized. So essentially we're going to see that negative crystallization peak, Tc, because that's the amorphous crystallizing into the crystalline form. So we see that. And then if you go high enough, that stuff that's just crystallized can melt, and that's the melting peak. And so Tm. And so that's the kind of curve that we would expect with this kind of material. All right, so that's kind of scenario one. So let's look at a different scenario where it's already crystallized. So we have a crystallizable polymer, but it's already crystallized to sort of the maximum extent that we would expect. And so this is these are semi-crystalline polymers, because we never expect it to be 100%, but there's always an amorphous component. So up here there's amorphous, and even down here there's going to be an amorphous component. So in this case, if we draw the same plot and look at what we expect, then again, there's going to be a TG, because there's still a certain fraction that's amorphous. Because again, even the most crystallized polymers are still 80-90%, so there's still a fraction that's amorphous. This step might be smaller because of that, but we still expect to see that. The main difference is, if it can't become any more crystallized, then we wouldn't expect to see this. And so instead of that peak, we don't see anything in that region. And so then, when it gets to the melting temperature, everything that's already crystallized melts. And so we see a peak there. And again, since it's already crystallized, this tends to be bigger than the one up here, because more of that material is crystallized. So Tm, so the enthalpy tends to be larger, and then doesn't have this crystallization peak. And this would probably be a smaller step, so it might be hard to see if it's there. Right? So those are a couple scenarios that we have. And the reason I bring this up is because these experiments tell us about the crystallization, and in essence we can figure out how crystalline something is. So we can figure out that percent. So how much crystalline phase, how much amorphous phase, and that's really important for polymers. Some polymers, the only difference there is the amount of crystallization. Low density versus high density polyethylene, the only thing that separates those is, other than the basic structure, is how much they can crystallize. And so this is an important characteristic. So when we have this scenario up here, the fraction of crystallinity we can get from looking at the melting enthalpy of the sample versus, so this is the absolute value of the melting enthalpy of the sample, minus the crystallization. So I'm putting the M for melting, C for crystallization here, so I can denote sample as well, over the melting enthalpy of 100% standard. So this is the enthalpy of a 100% crystalline sample of the same material. So this is something that you typically have to look up as a reference value, because this is in a lot of cases theoretical, and so we can't calculate this directly, and so we'd have to look this value up. So when you're thinking about these calculations for crystallinity, we can't do this until we know what material we have. So the initial part of this lab is to determine what it is, and once you get to that step, then in a lot of cases you can find this value and calculate the crystallinity. All right, so that's how we would do it for if this crystallization occurs. If it doesn't, if we have something like this, then it simplifies to just the melting enthalpy of the sample over the melting enthalpy of the 100% peak. And then if we want to get percents, we would just multiply by 100. So basically it just cancels out this peak. So it's really the same equation, but this goes to 0. So this is kind of later in the experiment. Once we have an idea of what our materials are, we can determine this if we have one of these crystalline polymers.